this is supposed to be pretty basic. This is the introduction, where I introduce probability to an undergraduate course. It's a little bit different than the way probability is introduced usually. Okay? And I believe this way is better. Okay? Now I say the holy Bayes theorem of Laplace. See, this Bayes was a reverend in the Church of England, and he wrote something remotely similar to what we call Bayes' theorem today. In fact, the person who really appreciated Bayes' theorem and used it was Laplace, who was not a religious man at all. In fact, when he finished writing his Mécanique Céleste, Napoleon asked him, but Pierre Simon, how come you don't mention God here and you talk about the planets and all that? And Laplace responded, I didn't need that hypothesis. So he was very pretentious, and he didn't believe in ghosts. So he's one of my heroes. In that sense, I believe that instead of being called Bayesians, we should be called Laplacians. I mean, Laplace was much cooler than Bayes. Okay, let's start from logic. Okay. Logically speaking, 1 plus 1 equals 1. And that is because the algebra of logic, this shows the algebra of logic is very different from the algebra of real numbers. By 1 here, we mean total truth, a true proposition. So the main difference with the algebra of numbers and the algebra of propositions is that in the algebra of propositions, you have a maximum truth. It's bounded. 1 plays the role as infinity. Once you get the whole truth, you cannot add to it. Once you get the whole truth, that's it. You arrive to the maximum, and 1 plus 1 is still 1. The algebra of propositions is similar to the algebra of numbers, but in fact, what we call the logical sum corresponds to the OR operator, the logical propositions. And there you see that if you have a false proposition or a false proposition, then the new proposition that you end up with still false. But if it is false or true, then it's like 0 plus 1 is 1. But when you have true plus true, true or true, you still have true. The negation corresponds to the not, and the logical product of logical multiplication has a table of the operation exactly the same as when you multiply zeros and ones. I mean, false times false, or false and false is false. False and true is false, so you multiply by 0 when you say false. But if you have true and true is the only one that you have true. Now, the Boolean, this is called a Boolean algebra. I mean, objects that can be manipulated and combined. You can make formulas by addition and multiplication and negation. So you get these formulas that form an algebra that's called the Boolean algebra. And this Boolean algebra is the algebra of propositions, but it's isomorphic. It's exactly the same algebra as the algebra of sets. So if you replace proposition by set and the true proposition by a given universal set that you call it, the universal set would be the true proposition. The false proposition would be the empty set. And then you can replace the addition by union of sets, and multiplication is nothing but intersection of sets, and negation is nothing but complement relative to this universe. So the algebra is totally identical, and that's why the algebra of probabilities that we're going to go into in a moment can be written either with sets, which is the traditional way after Kolmogorov, or with logical propositions, which is what James and more and more people now are advocating, because it really shows what probabilities are. So the probability is what we call the logic of science, because I mean the Boolean algebra of propositions just deals with complete truth or complete falsehood, and we know in life nothing is like that. Everything is right in between, is gray. We make an experiment, we have a hypothesis, the experiment doesn't completely prove it. It doesn't matter how great the experiment, we always have room for maybe it isn't so. Okay? So the logic of probability is really the logic of thinking for manipulating all kinds of thoughts. In fact, some of us believe that it's even underlying mathematics itself. So, say, even mathematics is not absolute certainty. So, for example, the interpretation of a probability then is, for example, here suppose the probability of heads, the canonical probability of heads, conditional on that you're flipping a fair coin. That you're almost saying that the probability of heads is 1/2. What does it mean by a statement like this? By a statement like this, we mean that the truth value of heads in the domain of this course of flipping a fair coin is not true and is not false, is something in between. It's an extension of the two-valued logic. The logic of probability is nothing but an infinite valued logic between 0 and 1. In the extremes, you recover the rules of Boolean algebra, but in between, we have these rules of probability. And the rules of probability, somebody proved only in 1948 that if you want to marry the Boolean algebra of propositions with the algebra of real numbers, there is essentially one way of doing it without making contradictions along the way, and that is, those are the rules of probability. That's something very powerful. In fact, that's not quite so, because what this guy proved is that if you assign your partial truths in any way you want, so that you're not going to end up in contradictions in the extremes when you have truth and false only, then no matter how you do it, if your system is removed from having contradictory statements, then there exists a way of regraduating your assignments of partial truth, so that in this new scale, the laws of probability are satisfied, the usual laws of probability are satisfied. For example, one of the things that you can end up with a completely equivalent theory of probability, where the probability of the whole thing is not 1, it's infinity, for example. But the law of addition and multiplication gets much more complicated. When you assign your partial truths just in the interval 0, 1, then that regraduating function allows the laws of probability to be much simpler. In fact, there are only 2 laws of probability. I mean, you go to the library, there are books and books on probability theory. Everything is just deduced from these 2 laws, plus a teeny tiny mathematical icing on the cake, continuity. But the basic laws of probability are just these 2, the addition rule and the product rule. The addition rule only says that probabilities are amounts of truth. That when you say the probability of something given something else, conditional something else, what you are getting is just think of this as mass, as physical mass. You're weighing, but it's not physical mass, is amount of truth. It's an abstract weight that propositions have. If propositions are very, very close to true, then you have a lot of weight. If they are close to falsehood, then you have very light weight. And also, the other important thing here is that probabilities are always conditional. There is no such thing as unconditional probabilities. I mean, if you look at books on this typical probability theory, they will tell you that that's not the case. But the only thing is that when you don't write the conditioning, you're just implicitly assuming that you're conditioning on the trivial truth of the sample space. So probabilities are always conditional on a statement that you call the certain statement. Okay? Now let's look at the sum rule is pretty natural. It just says that the probability of the logical sum is the sum of the probabilities, provided that these 2 probabilities do not overlap. I mean, these 2 propositions do not overlap. What does that mean? It means that the proposition A and B is true conditional on C cannot be true. I mean, there is no truth in common to A and B, so that this as the truth do not overlap. In fact, this law, the sum law, is shared by every concept that quantifies amount in mathematics. For example, which concept quantify amount in mathematics? Length is an amount of length. That if you have two sticks that do not overlap, two separate sticks, the total length, when you put the two together, when you have the two together, is the length of one plus the length of the other. The same thing is true for number of elements. Two sets that do not overlap. You count the total number of elements of, when you add the two sets, it's just the number of elements this plus the number of elements of that. Area, volume, hypervolume, physical mass, all those are amounts. And they satisfy this rule that share with probability, because probabilities are nothing but amounts. Amounts of truth in a given domain of discourse. The C, is always there, is the certainty probability or the certainty proposition, or the domain of discourse, the context in which the propositions acquire their truth values. Well, the sum rule is pretty obvious, but the product rule, which can be deduced, I mean, you cannot fool around with this product rule, just says how to assign the probability to the logical product, to the conjunction, the probability of A and B given C, in terms of the individual probabilities of A given C and B given AC. I'm going to give you a demonstration that those of you that are not familiar with this, it's in fact pretty natural to have this product rule. Okay? And this makes sense provided that AC given C is not false. In other words, that you are not conditioning on a contradiction. What you are assuming, or also you're assuming in a context that you assume true. So if that context is what is called in logic a contradiction, that it cannot be true in any domain of discourse, then this doesn't make any sense, because it's like divided by zero. Okay, so for example, let me give you a graphical demonstration of the sum rule. The sum rule, typically, when you use the isomorphic algebra of sets instead of propositions, then you describe the event or the logical proposition that something in this area happened with a part of an area like that. So, and the size, the area, is supposed to encode or represent the amount of truth. The bigger the area, the more truth there is. And when the two sets do not overlap, that means that A and B, I mean the intersection of A and B, is the false proposition in the domain of discourse C. The domain of discourse C plays the role of the universe set here. So that only says that it's like areas, the addition rule. The product rule is a little bit more complicated. For example, suppose that we have a box with 3 balls in it, 2 blues and 1 red. And we want to compute, the experiment consists of the following. You take 1 ball at random, every ball has the same chance of being chosen, and you take it out. And then you don't put it back. Then you take the second ball at random. Now I want to compute the probability of getting the first a blue ball and then the second a red ball. So what is the probability of the logical proposition? The first ball is blue and the second ball is red, given this domain of discourse, given what I just told you, that we have a box with 2 blues, 1 red, we are taking the balls at random, that we are not putting it back. Conditional on all that, that's my certainty, is a conjunction of many things that I assume to be true. I want to compute the chances that I get that. Well, according to the product rule, it tells you exactly what. So is the probability that you get a blue the first time? Well, what is the probability of getting a blue the first time? You have 2 out of 3, so it's 2/3 the chance of getting a blue. And then times, given that you have gotten a blue, I mean, you have already gotten a blue, the chance of getting a red now the second time is just 1/2. You just changed your domain of discourse. You changed the things that you're talking about once you assume that you have chosen the blue first. And in fact, that's exactly what happened. I mean, the fact that we get the 1/3 for this is pretty obvious because, I mean, every possible sequence of two balls can be observed, and you can see here you only have three possibilities: blue, 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 red, or red, blue. So the chance of that is just 1/3. So it matches that the product rule it matches our intuition with what probabilities are. But this is not just intuition. The incredible thing is that these two rules are the only way of marrying real numbers to Boolean algebra. So, because of that, we're going to deduce in 2 lines Bayes' theorem, which this trick I saw for the first time in James's book. And if you look at the demonstration of Bayes' theorem everywhere, I mean, it's a mathematical triviality. So I'm going to show you it's just something very, very simple. Let's think about all the propositions, all the possible things that we can talk about or we can think. And let's divide them in 3 categories. Some of them we're going to call theories or hypotheses, and usually theories and hypotheses are denoted by H for hypothesis, or hypothesis 1, H sub 1, or sometimes when we're going to continue we label things with parameters, so things are theories also. So we have theories, we have facts. Facts are the data, the things that we observe. You put your measurement there, the neuron fires. I mean, these are the things, the objects that our senses have, or the data. But you see, we are only dealing here with propositions. So here's another thing that I don't think is very common, that data is the logical proposition. The number 2.7 is not data. It's only data when it's interpreted as a logical proposition. The result of such and such an experiment produces the number 2.7. Then 2.7 is data. 2.7 in the abstract is not data. Now, that you may say, well, what's the relevance of that? That, I think, is extremely relevant because that shows, since if data is a logical proposition, there are no logical propositions in the vacuum. All logical propositions acquire its truth value in the domain of discourse. Therefore, there is no data in the vacuum. All data is conditional on your theories. It's conditional on your prior conceptions. So you cannot see naked data. Therefore, data and theory are entangled. You cannot disentangle completely data and theory. Data is theory laden, and theory is data laden. Okay, so we have theories, we have facts, or observations, results of experiments, and we have prior information. I like to denote prior information with this all here, because it's like an origin. And in prior information, just we sweep under the rug with everything. Everything else is prior information. Now, according to Bayes' theorem, see, there is no constraints on these things being, this can be any logical propositions whatsoever. So, since the AND operator, or the conjunction, is commutative, that means A and B is exactly the same as B and A in any domain of discourse, then the amount of truth in H and D, conditional on my prior information O, is going to be the same as the amount of truth in D and H. Just apply the product rule on the left-hand side and the product rule on the right-hand side, and according to what we just saw, the probability of H and D conditional on O is the probability of H given O times the probability of D given H and O. Just changing the domain of discourse here. And you do the same thing here, but the other way around. So because we start with D, probability of D given O, and the probability of H given D and O. Now just solve this little equation. These are real numbers now. A number times another equals a number times another. We can solve like that, and pass to the other side, basically. And we get the unbelievable Bayes' theorem. Now, this is something that I cannot emphasize enough how useful this stupid piece of mathematics is. First of all, anybody who has a problem with that theorem has a problem with the commutativity of the AND operator. you don't want to have a problem with a computer, you will have a problem. You don't. Because if you do, then you belong to a madhouse. So, because of the commutativity of the add operator, we have this statement here saying, what is the relevance for it? Well, I claim, I'm not the only one claiming this, many people are claiming this because it's obvious, as you see it, that anything that makes sense in statistics, anything, or everything, is a consequence of this little statement here. Period. Now, how do you interpret that? What's the interpretation of this? The interpretation of this is the following. Everything here is so important that everything has a special name, see? And there are even names in Latin. So, what we call the probability of the theory, given the prior information, is what is called the prior probabilities, or a priori probabilities. Is the amount of truth that you assign before the facts, before you conduct the experiments. Okay? That's called the a priori probabilities. These are the prior probabilities for the theory. Okay? For example, you can plug into theory, say, general relativity. What's the probability of general relativity before you conduct the experiment of observing the curving of the light around Mercury? Or was it Mercury? No, it was the perihelion of Mercury. It was the precision of the perihelion of Mercury. So, before that experiment, general relativity was a theory already. And how you compute that prior probability, that's another question. But we're going to, if we continue meeting here, we're going to see ways of assigning prior probabilities that make sense. But supposedly that you can do that, then a priori, before the experiment, before conducting the experiment, the chance for that theory was given by this number here, P of H, given out a priori. Now, after you conduct the experiment, that is the a posteriori probability of the theory. That's what is called posterior for short, or probabilities after the fact, after the experiment. Is given by this formula here. You have to combine the prior probability with what is called the likelihood of the hypothesis. The likelihood of the hypothesis is interpreted as a function of the theory, H, for given data. You collect the data, you plug that data in here, and then this becomes a special function of H. As a function of H, that's called the likelihood of the hypothesis, H. Usually, that comes to you with the specs of the theory. Actually, having a well-defined theory means having some way of telling me what are the chances of the different pieces of data that I can observe for given experiments that the theory says that make sense to perform. So, given the theory of general relativity, if I assume that general relativity is true and my prior information, then I know what's the chance of observing the precision of the period of Mercury being in this range or in that range. The theory tells me that it should be around this range, and with some error of experimental error, then I know the chances of that. Theories usually, in fact, we say we qualify a theory to say it's well defined if it allows you to produce the chances of the different pieces of data produced by experiments, conditional on the theory being true. That's the likelihood. You multiply by the prior. This thing here, if you think of it as a proportionality constant, because it doesn't depend on age, is just something that can be, in principle, obtained after you do this multiplication here, in such a way that the addition over all possible competing theories that you have equals 1. So this is usually, this usually, it's not, you don't even need to write it down, because it can be recovered, or sometimes it's irrelevant. It's called the evidence of the theory. Okay? So the evidence in your data is given by this proportionality constant here. So the claim is that all correct statistical methods follow from the application of this. This is a learning theory also. I mean, you don't have data, you have prior assumptions, you collect data, you update your prior assumptions, your prior assignments of probability according to that rule, so that you learn something. This is how the way we learn. Well, and that's about it. Okay.